Okay, hi everybody. So in this lesson, we're going to take the previous work that we've done just one step further. We're going to talk about function notation. Okay, there's a way of writing relations that are functions that allow us to work with them a little bit easier. Okay, and this is this thing called function notation. And so what we're doing here is we're going to rewrite functions like this. So it used to be that we would write like y equals some expression here. Now we're going to write this little f parentheses x parentheses here. This is read as f at x or f of x. Okay, it is not multiplication here. And I know sometimes we will see that as multiplication when we have two things together with parentheses there. In context, though, you would know that this is not multiplication. So what's happening here is, just like it says here, y is the output, f is the name of the function, and actually there's a little bit more to it than that, and x is the input. X is the independent variable, but I want to talk a little bit more about the f of x in function notation, okay? So if you take a look down here, just to see what's going on here, in this little box right here, in the first one here, normally up to this point, you've probably seen it as y equals 2x minus 1. Well, now what we're going to do is we're going to replace that y with this notation f of x is equal to 2x minus 1. Okay? Now, we usually use f of x when we're dealing with just x's and y's. So, and we use the letter f because it's a function. Okay? Now, but if you've got a different function here, you can use whatever variable you want here. So for example, d equals 30 times t would be d of t is equal to 30 times t. So notice that the independent variable shows up inside there. So these two variables are the same here. Down here, c is equal to 12n plus 5. Well, c of n is equal to 12n plus 5. Okay? Now, I want to talk about this function notation, the f in the function notation just a little bit more here. F is not just the name of the function. I'll put it over here. F, okay, F is the rule. It represents the rule that you're applying here. So, for example, in this very first one up here, the F stands for this rule. So what I'm going to do here is I'm going to quickly just take a look at this. What's going on here? So F stands for multiply the independent variable by 2 and subtract 1. Okay, so F is the name of the function here, but it also is representing that rule. Multiply the independent variable by 2, subtract 1. That's exactly what we're seeing here. And then this part of the notation, whatever shows up in parentheses, okay, is the independent variable. So the independent variable here is x. So when you put those together, multiply the independent variable by 2 and subtract 1, and you put that together with that little bit of information inside the parentheses here, then we're seeing, oh, 2 times x, the independent variable, minus 1. Okay, that's what that means. So for example, in this next one here, we might write it like this. D here is saying multiply the independent variable by 30. That's the rule. Now, in this particular case, when you write it like that, when you write t here, we're saying here the independent variable, then that means 30 multiplied by t. But for example, I could have very easily written it like this, d of x. D still stands for the rule, multiply the independent variable by 30. It's just that now what I've done is inside the parentheses is the independent variable. So this would now be 30 times x. It's just that's substitution. Whatever's inside the parentheses takes the place of the independent variable in the expression. Okay, in this last one here, C, what does C stand for? Well, it stands for multiply, the independent variable by 12 and add 5. And then what we're seeing here is that inside the parentheses is n, So we're being told the independent variable is n. Put that together, and it's 12 times n plus 5. Okay? But then I could change this for example. I could change the notation here to be something very specific. I could write, for example, C of 2. And so now what I'm doing is I'm being very specific with the value of the independent variable. So C hasn't changed. The rule hasn't changed. Multiply the independent variable by 12 and add 5. It's just that now, instead of a variable inside there, I put a 2. So the independent variable right here, this independent variable is now 2. So what does that mean? Multiply the independent variable, 2, by 12. So I get 24. So this is going to be 12 times 2. And then add 5. So 12 times 2 is 24, plus 5 is 29. So now I've got this little expression here. Okay, C of 2. Oh, it's having a hard time seeing what I'm writing here. Hold on a second. I'm just going to move this up just a tad here. C of 2 is equal to 29. In other words, and what's awesome about this notation is it condenses things a little bit when I write it like this. So here's my independent variable. Here's the dependent variable. So this tells me immediately that the point 229 is on that particular graph. Okay, there are lots of different reasons why function notation is so useful here, and I've probably gone way over and above what I needed to with this explanation. I hope I haven't confused you with it, and I probably have, quite honestly. But what we find is as people progress kind of through high school, in many cases it becomes very clear that by the time they get to grade 12, that they weren't really all that clear on what function notation meant, okay, and what was going on inside the parentheses there. Okay, that is the independent variable. Whatever's inside there replaces the independent variable in the expression. Anyway, let's take a look at some examples here, and hopefully that will help clarify things. Okay, so here we go. So the question says, write the following in function notation. So this first one I see here is y is equal to 2x minus 1. Okay, that's a pretty standard way of writing that. So typically what we would do in this case here is we would simply use f of x, and we would replace that y with that f of x, and there we go. So f of x is equal to 2x minus 1. For this next one here, notice that my dependent variable is s, and my independent variable is t. Now, because this isn't y and x, I can name this with the s there, the dependent variable here, and make this s of t, because remember, I want to put the independent variable inside that notation. Just like over here, I need to express what the independent variable is. And then that is going to equal 8 times t. Okay. At first, the first time you start working with this, it might look like we're making this more difficult. Okay, the notation is getting a little bit more complicated, but you are going to see through use that this is actually simplifying things a bit. So let's take a quick look at some other questions here. So given that g of x is equal to 3x minus 1, so what this is telling me here, what g is, okay, in this particular case, g is multiply the independent variable, what was that, by 3, and subtract 1. Okay, multiply the independent variable by 3 and subtract 1. So when I see this over here, this g of x, I know that g means multiply the independent variable by 3 and subtract 1. And then this is telling me that the independent variable is x. So that is 3 times x minus 1. Now it turns out that is equal to 2. Okay, that's what that 2, I don't do anything with the 2. I don't put the 2 inside the g of x there. I don't replace that with it. G of x, this right here, is equal to 2. And now this becomes an equation that I've solved before. So the first thing I'm going to do here is bring that 1 over to get 3x is going to equal 3. And then I would divide both sides by 3 to get x is equal to 1. But this next one is different. This next one says g of 4. Now, remember, G is multiply the independent variable by 3 and subtract 1. And then whatever's inside is the independent variable. So what this means is multiply the independent variable by 3. So it's going to be 3 times 4 minus 1. And now this is just an evaluation thing. So 3 times 4 is 12 minus 1, or 11. So when you see a number inside here, this is an evaluation sort of a question. But if you see the x in there equal to a number, okay, this is a solve sort of a question. So over here, when I see g of x is equal to -1, okay, I know that this is actually going to be a solve sort of a question. So g of x, multiply the independent variable by 3, which in this case is x. So 3 times x, subtract 1 is equal to -1. So I would add 1 to both sides, and that's going to get me 3x is equal to 0. And then divide by 3, and I get that x is equal to 0, which is fine. That's an okay answer. Don't get thrown off by the fact that you're getting a 0 there. That's okay. The next question says, given that f of x is equal to 2x squared minus 5, evaluate the following. Okay, so what f is in this case is it's square the independent variable, multiply by 2, and subtract 5. That's what the F rule means. So now over here for this first one, notice I've got f of x is equal to 1/2. So I'm putting a variable in as my independent variable, where the independent variable goes. It's equal to a number. This is going to be a solve sort of a question, because f means square the independent variable, multiply it by 2, and subtract 5. And that is telling me what the independent variable is. So take the independent variable, which is x here, square it, multiply by 2, subtract 5. And then the equation here tells us that that is equal to 1/2. So now this is an equation like I've worked with before that I can solve. I'm going to add 5 to both sides. That's going to be 11 over 4. I'm going to need common denominators to do that. I'm going to divide both sides by 2. So it'll get me x squared is equal to oh, sorry, and I'm sorry, I made an error there. I anticipated where I was going with this particular problem here. That's not 4 there, sorry, that should have been a 2. Yeah, when it becomes 1/2 plus 5 is going to be 5/2, or 11 over 2. And then I divide that by 2, I get 11 over 4. And so now I got to take the square root of both sides, which will get me plus or minus 11 over 4. Which is, if you go and take the decimal here, approximately 1.66. So that's my value for x there. So again, when I've got my function notation with the x in it equal to a value, that's like a solve sort of a problem here. However, if there's a number inside, this is an evaluate sort of a problem. So f is square the independent variable, multiply by 2, and then subtract 5. In this case, the independent variable is -2. So square the independent variable, multiply by 2, subtract 5. So the first thing I'm going to do is that squaring. So that'll be 4. Then I'm going to do the multiplication, 8, and then subtract the 5 to get 3. And then this last one over here, again, because of the way this is set up to get me to solve this. So f of x is going to be 2x squared minus 5, and that is set equal to 0.4. So now I'm going to add that 5 to both sides to get 5.4. Divide both sides by 2 to get 2.7. And so x will equal the positive or negative square root of 2.7. Now remember, every time I take the square root like that, I got to include the plus or minus there. And then I'm just going to go to my calculator, and I will get that is approximately 1.64. Okay, so there you go. Now this is one way that this problem or function notation can be addressed here. But because of the work that we've done with representing relations and functions, there's another way that this could be represented. We could also look at this graphically. Okay, actually I'm going to need to move this up just a tad bit more. Okay, now here, h of 8. So what we're seeing right now is this graph, this blue line that we're seeing here, this is my y equals h of t function. Okay, so notice we've got t down here and we've got h up here. Okay, h of 8. I don't know what the equation is for this particular relation. But that's okay. This notation doesn't require that. H of 8 is simply telling me if the independent variable is 8, and remember, the independent variable is along the horizontal axis. That's this guy right here. If that's equal to 8, then the whole thing here is the dependent variable. So what's that equal to? So we go up. Oh, and we're not quite at 6. We're just a little bit less than 6. We're just going to approximate that. So let's say 5.8. Not quite at 6 there. Okay, so approximately 5.8. Now, on the other hand, if I tell you h of t is equal to 10, remember, this is an equation that you're solving. So I'm looking for where basically where that y coordinate is equal to 10. So that's up here. Right there is where we hit 10. And going straight down here, that is going to be where t is equal to 0. Now, the independent variable here, well, the independent variable goes inside the function notation. It's also on the x-axis here. So the independent variable here is going to be t. The dependent variable is typically what's outside on function notation, okay, right there. It's also on the vertical axis there. So that's going to be our h. Now, is this data discrete or continuous? Well, it's continuous. Now, how do I know that? Well, because if it was discrete, what I would see would be dots, disconnected dots. But I don't. This is a smooth line. Everything's been connected here. So it's going to be a continuous graph here. Now, the next question is asking for the y-intercept. Remember, this is the value. This is the point where it crosses the y-axis. So in this case right there, that is going to be 0, 10. That is this point right there. Now, in fact, you will see sometimes people, because we all know that the intercept here, the y-intercept, is the place where the x-coordinate is 0, sometimes we won't even expect you to answer that. Sometimes just the answer 10 is okay. Similar with the x-intercept, we're talking about where we cross the x-axis, okay, where the y-coordinate is 0. So this would be 10, 0. When I ask for the x-intercept here, I know that the y-coordinate is 0. So sometimes it's okay just to write the number there, just to write the 10. Either way, you kind of have to figure out what your teacher's expecting there. Okay, and now finally, with this question right here, we're going to interpret some the data in graphs here. So we're going to use the diagram here to answer these questions. So the question here is says that Judy recorded the money she saved in dollars every week for 10 weeks. So the results are as follows. So there's her graph right there. I'll move this up just a little bit more. So using that information here, how much money did she save at 9 weeks? Okay, so at 9 weeks, now bear in mind, that is going to be a value for the independent variable. That's down here. So we kind of slide up here, and what does that give us? That looks like $75. Okay. How many weeks did it take to save $50? Okay, so in this case right here, this is now a value along the vertical axis, so 50, that's right here. So now I'm going to kind of work this in reverse. I go back to the graph here. I hit that point. Then what is that? That's 4 weeks. Now, what is the dependent variable? The dependent variable is on the y-axis here. This is going to be the amount. And so when we ask this, what is the dependent variable? Please don't answer y. Or don't, if you can do better than that, please do better than that. This is the amount of money saved. Okay? That's what the dependent variable is. That's what depends on the time here. Now, okay, I think there's something missing here. Yeah, this probably should have been like the amount of money at 6 here. Okay, What is A at 6? Because we're talking about function notation here. I think they just missed the A there. So they're giving us the independent variable here at 6. So we go here, here's 6, and we slide up. And when we slide over, we find out that A of 6 is equal to $60. And then finally here, question is, what does the y-intercept represent? Okay, the y-intercept, first of all, let's identify what it is. Okay, the y-intercept is going to be the point on the graph where it crosses the y-axis. So that's the point 0, 30. And so let's just talk about what that says here. That says here at time 0, the money saved is $30. So basically, and this is going to be true for a lot of applications where time is on the x-axis here. This is the initial, and that's the key word here, the initial amount of savings.